And we are live. Hello, I'm Doug. This is a dog. And we are going to do a lesson on systems of linear equations, hence the title. This is a Barcelona shirt. It's quite shiny, isn't it? And it's about time I started with the math. So the dog is going to sit here and be good in the armchair and watch me politely, right? Sit, stay. That's your role here. Stay. Lie down. Good girl. Okay, so we can get started. The challenge here is I want to do a lot of examples, but systems of linear equations are kind of a little bit bigger problems. So it's not like the sort of situation where you can make up an example every 30 seconds. The way I decided to do this was by doing 4 systems, but I'm doing each system 3 times, showing them 3 different methods for solving it. So what am I talking about? A system of linear equations is a situation where you have 2 or more straight line equations, and the solution set of the system is the points of intersection of those lines. I'm not going to do any systems with 3 lines or more. I'm only going to do systems with 2 lines. Now, we are used to the y equals mx plus b form for the equation of a straight line. So we are going to use that a lot, but the equations don't always come in that form. Let's get into our first example right away. And the first method I'm going to use for solving it is graphing. So I have 2 equations. Let's see where I'm going to write this. So equation 1 is 2x plus y equals 10. And equation 2 is x equals y plus 2. Okay, now neither of these are in y equals mx plus b form, so we get to use our algebra skills right away and get them into that form, because it's going to be very useful, as usual, to have these equations in the form y equals mx plus b. It makes it faster to graph them, but it's useful in other ways too, as we experiment with these 3 different ways of solving. So solving, these are 2 lines. They cross somewhere on the graph. I want to know the point of intersection of the lines. I want to know the point where these lines cross. So I'm going to solve this first by graphing. I'll start by getting them into y equals mx plus b form. Equation 1, I'm going quickly with the algebra here. We have 2x plus y equals 10. It's almost in y equals mx plus b form. The problem is that the 2x is over here, and I want it on the other side. So if I subtract 2x from both sides, I end up with y equals negative 2x plus 10. I could write 10 minus 2x if I want, but then it wouldn't really be in that form mx plus b. So I do it this way so that the x term happens before the constant term. That was fast. The second equation, this is a cute trick with an equation, because an equal sign is like a mirror and x equals y plus 2 means the same thing as y plus 2 equals x. I'm going to start by writing it backwards. Y plus 2 equals x, and then if I move this 2 to the other side, I'll have the y equals mx plus b form I want. So what I'm doing is I'm subtracting 2 from both sides. Y will be isolated, and I'll have y equals x minus 2. Now we can graph. So we're going to use our shortcuts as much as we want to, because we don't want this to take too long, because we want to do a lot of examples. So let's get a graph ready. And it's a little bit crooked. I'm not using a mirror, but I'm just going to do my best. I need tables of values so that I can graph these lines. But of course, tables of values are very quick to make when you have your equations in y equals mx plus b form. It's one of the reasons that we like to do that. So I'll do 3 points for each line like I'm used to. If x is 0, negative 2 times 0 cancels, and negative 2 times 0 is equal to 0. So y will end up being equal to 10. If x is 2, negative 2 times 2 is negative 4, and negative 4 plus 10 is positive 6. It is fast to do a table of values when you have this form. And if x is 5, negative 2 times 5 is negative 10, and negative 10 plus 10 is equal to 0, so y is equal to 0. That quickly I have a table of values for this first line. And it will also be quick to do the second table of values for the second line. If x is 0, is that what I started with? Yes, it is. If x is 0, I have 0 minus 2, that's negative 2. My y is negative 2. I am doing algebra, I'm just not showing all of my steps as much as I usually do because I want to get these graphed. If x is 2, then 2 minus 2 is equal to 0, y is equal to 0, and to do a third point, I always like to do a third point just to make sure. If x is 6, y equals 6 minus 2, which is 4, my y is 4. I can graph these lines. Let's do this quickly. First line, 0, 10. Let's say I decide 10 is up here. 0, 10 will be right there. I'm going to scale my graph proportionally so that if that's a 10 there, then I would want 10 to be about here on the x-axis. Let's make my graph a little bit more appropriate though by identifying my axes. The 0.26 therefore is going to be something like this, and the 0.50 is going to be about here, and we can draw this line. Then we look at the other table of values. 0, negative 2 will be about here. 2, 0 will be about here. And 6, 4 will be about here. And then I draw a line that goes through those 3 points. I have graphed my 2 lines. I'd like to label them. So I'll label them line 1, like 2, the way I labeled the equations to start with. And now I'm estimating where they cross. But this is graphical methods, so it is an estimate, especially since I didn't use a ruler. I'm looking at this and I'm trying to judge where these lines cross. I'm saying that looks like x equals 4, y equals 2, this point of intersection. That's the solution set, that's the answer. And then I can test to see how well did I do this. If I did it on graph paper, my chances are better to get it right on. But I'm going to test it by plugging the 0.42 into one of the original equations. Well, actually, I should plug it into both of the original equations. So, if x is 4 and y is 2, this becomes 2 times 4 plus 2 equals 10. 8 plus 2 equals 10. That's true, it verifies. If x is 4 and y is 2, this becomes 4 equals 2 plus 2. And yes, 4 equals 2 plus 2, so that also verifies. It means my estimate by looking at my graph was good. That's one method. This is the graphical method for solving a system of 2 linear equations. It is kind of rushed, I admit it, but we're going to look at this situation again because I want to use the same 2 equations to show a different method, an algebraic method for solving this, where you don't have to rely on looking at a graph and hoping that you drew the lines really straight in order to get a good answer. I did get a good answer this time, but I kind of set myself up. I kind of knew what was going to happen. Let's erase some of this, but we'll leave the 2 equations and we'll try using a second method to solve, to find the point of intersection. So I'm just erasing everything except the original 2 equations, and we're going to use the elimination method now. I'm taking a look at the time, seeing how well this idea is going to work, of trying to do all of these examples in the 1 hour I planned for this lesson. There's still a chance that I can make it work. Let's see. Okay, so elimination is a method where we want our equations in the form ax plus by equals c, which is lucky here because this equation is already in that form. This one, it's close, but it's not quite there yet. So I'm going to do some algebra to this equation to get it into that form. And all that's going to happen is I'm going to subtract a y from both sides so that this y becomes negative y on the other side. So I'll show that. X minus y equals y minus y plus 2. But of course these y's cancel. So I have x minus y equals 2. And it's in that form. Ax plus by equals c. I'll take the 2 equations and I'll write them in that form. One right below the other. X minus y equals 2. And then what I do is kind of a weird trick. Seems weird to students the first time they see it, I think, which is I add the 2 equations. Now the reason this is going to work is because when I add the 2 equations, the y's are going to cancel. That's a little lucky. You can't always expect any 2 equations you want to find the point where they cross to have a positive y in one equation and a negative y in the other. It happened this time because it's a basic example, but if it's not happening by itself, there are tricks you can do to make it happen, and we'll see that when I do some further examples. But when I add the x's, add the y's, and add the numbers, 2x plus x is equal to 3x. The 2 y's cancel. and 10 plus 2 is equal to 12. I'm very close to figuring out what x is equal to. The reason this trick works is because we had two equations that each had two variables, x and y, but our little trick of elimination where we added them and the y's cancelled resulted in an equation that only has x and that we can solve. So if I divide both sides by 3 using all the algebra skills that I've been brushing up on for weeks now, these cancel, x is isolated, 12 divided by 3 is 4. I have the x coordinate of my answer. How do I find the y coordinate? I take either of the original equations and I plug x equals 4 into it and solve for y. So I can choose whichever one I want. I'm going to choose 2x plus y equals 10. If x is 4 though, this becomes 2 times 4 plus y equals 10. 8 plus y equals 10. I'll subtract an 8 from both sides. These cancel, my y is isolated, 10 minus 8 is 2, I have y is equal to 2, and then I have to remember to write down my answer. The answer is the point at which the two lines cross. It has an x coordinate of 4 and a y coordinate of 2. It's the same answer I got from the graphing method. But the graphing method depends on me graphing carefully, drawing my lines carefully to get a perfect answer, whereas this algebraic method of elimination will always give you a perfect answer so long as you manage to go through the steps without making any mistakes. And what are the steps? The steps are algebra skills that we have been working on for weeks. So this is very convenient. It's a bit of a big question, the idea of systems of equations, because a straight line has two variables. And when you look at the y equals ax plus b form of it, do I have any of that? I don't have it written in that form. The y equals mx plus b form, the m is the slope, and the slope can be anything. The different numbers can make the line tilt different ways. The b is the y-intercept. The line can be going through the y-axis in all these different places, depending on what numbers are in place of the m and the b. So that's a lot of variety. A lot of things can happen with one line. And here we are taking two lines, taking two things that each have a lot of variety, and we're putting them together, and we're able to solve this puzzle. It's kind of cool that this method works so well, and the graphing method also works so well, because there are so many different things that can happen, but we are able to take control of it. That is elimination. That's one of the methods we need to know. Graphing, of course, is another, but there is a third method I want to talk about, which is substitution. And to do that, I am yet again going to use the same two equations, and I'm going to answer the same question, which means I should get the same answer. I'm expecting to get the same answer, 4 comma 2, x is 4, y is 2. But I'm going to get it by doing a different trick. And that trick is called substitution. Substitution is an algebra trick. It's another algebraic method, kind of like elimination, but we're just doing a different trick. And for substitution, we want to isolate either the x or the y in one of the equations. That is convenient here because in the second equation my x is already isolated. So that means if x is equal to y plus 2, then this x is also equal to y plus 2, so I will substitute this x with y plus 2. That's the idea of substitution. So this example is already set up so that I can quickly get into the substitution without having to do algebra first. But if I needed to do algebra first, well, I know my algebra skills, so I'll do it. And that will happen in some of our examples. Okay, so x equals y plus 2, therefore this first equation becomes this. I take away the x and I replace it with a bracket, and then I stick into the bracket what x is equal to in the other equation. And now I simplify. What happened here? I did a trick where I started with two equations with two variables, and I turned it into a single equation with only one variable, because this only has y now. That's the trick, and that substitution does that for you. Elimination also does that for you in a different way. Simplifying, 2y plus 4 plus y equals 10. 2y plus y is 3y. I'll subtract a 4 from both sides. These cancel. 3y is equal to 6. Then I need to divide both sides by 3 so I can isolate my y. and y is equal to 2. And we knew that was going to happen. And our answer, 2 is the y coordinate, so I write it into a coordinate pair after the comma. But I still need to know what my x is. Yes, I know, we all know what x is going to be. But I need to know, how do I show what it's going to be when I don't already know the answer? And I do the same thing as the last step of elimination, which is I take my y equals 2 and I substitute that into one of my original equations. This time I'm choosing the second one. X equals y plus 2, but if y is equal to 2, that means x equals 2 plus 2. It's another type of substitution that I'm doing here. Therefore, x is equal to 4. We have our answer. It is the same answer. We managed to do this system of these two linear equations with 3 different methods, and all of them told us where these two lines will cross. That worked, and I managed to do it in a reasonable amount of time, so I think I am going to succeed in doing my lesson plan. Now I'm going to pick 2 other equations, and again, I'm going to do all 3 methods. In the end, in this hour, I expect to do 12 examples. If you consider what I just did to be 3 examples, because I did the same question 3 different ways, I will do 12. 12 examples is a lot for me to pack into a 1-hour lesson, but is it enough for students to understand thoroughly and to be able to do this for the rest of their lives? I don't think so. I think we need to practice this a lot. Like I said, there are so many different things that can happen, all the variety of things that can happen with a single straight line equation with the slope and the y-intercept, all the different values they can have. And then when you introduce a second straight line equation, the number of things that can happen when you combine 2 lines together like this is there are so many different ways that the algebra can look, or that the lines can look on the graph, that you are not going to master this by doing only a few examples. It is a really good idea to do quite a few examples. Okay, so the first equation is 2x plus 4y equals 8. And the second equation, I'm going to write it lower down so I have more space to show my algebra, is y equals x minus 4. Okay, and of course we want to do this question by graphing first. So we want y equals mx plus b form. This one's already in y equals mx plus b form, but this one isn't. So what am I going to do? I'm going to use my algebra skills. How do I get y to be alone on the left of the equals when it has all this other stuff with it? Well, I'll start by subtracting 2x from both sides. I like to show this step, but students are able to go a little more quickly if they have practiced enough, and just show this 2x being subtracted from the other side. Sometimes I do it that way, and sometimes I like to show all the steps. If I'm subtracting 2x from both sides, I'm going to start by putting negative 2x here, and then write plus 8, because I know what I want. I want y equals mx plus b, so I want the x term to be before the constant term. These cancel. 4y is now isolated, but the y itself isn't isolated yet. But if I divide everything in this equation by 4, these cancel, y will be isolated. Negative 2 over 4x simplifies to negative 1/2 x. And 8 over 4 is 2, so I have y equals mx plus b form, y equals negative 1/2 x plus 2. Okay, now I can do my tables of values for both lines. For the first one, if x is 0, negative 1/2 times 0 is 0, plus 2 is 2, y is 2. If, I want to use the table of values I planned ahead of time. Okay, so if x is 2, why am I choosing 2 and not 1? Because I see that I'm multiplying by 1/2, so I get some canceling. Negative 1/2 times 2 is equal to negative 1, and negative 1 plus 2 is equal to positive 1. And if x is 4, same strategy. I'm using an even number because this will simplify more quickly. Negative 1/2 times 4. Well, half of 4 is 2. Negative 1/2 of 4 is negative 2. And negative 2 plus 2 is equal to 0. So I have the point 4, 0. That quickly I created a table of values. And this one will also be quick. If x is 0, 0 minus 4 is negative 4. So I have y equal to negative 4. If x is 4, 4 minus 4 is 0. Notice how I'm choosing values to plug in my x position, which will simplify easily and conveniently. If x is 8, 8 minus 4 is 4, y is 4. again, that quickly I have a table of values with 3 points in it, and I can graph the lines. Y-axis, x-axis, label them. Look at the numbers in my tables of values so that I can scale my graph in a way that these numbers will fit. If I decide the point 0, -4 is about here, this suggests the scaling that I need. I want to be consistent with that because I want to be able to get a good answer from reading the graph. 4, 0 therefore would be here. And 8, 4 would be about here. And I can draw a line through these 3 points. Not a perfectly drawn line, but for someone who's using no ruler, that's pretty good. The second equation, 0, 2 is going to be here. 2, 1 is going to be here. And 4, 0 happens to be a point that I already used in the other table of values. That's just luck. I draw a line through, and of course the point of intersection is going to be 4, 0. I want to label the lines. There's my equation 1, there's my equation 2. I have an answer. I use graphing to get the answer. And I have more confidence with this answer than I did with the first example, because not only did it really look like it's 4, x is 4, y is 0 when I look at the graph, but even if my graph were to be messy, I also have some other evidence right here, which is it just so happened that 4, 0 appeared in both tables of values. I didn't plan that, but when it happens, it helps me to see that my answer is probably correct. Okay, we have done the graphing method for the second example. I'm going to keep the 2 equations, and I'm going to do the elimination method with these 2 equations. And there we go, we're ready to do that. Okay, elimination, we need ax plus by equals c, and we got lucky again. The first equation is already in ax plus by equals c form. This one isn't though. So if I subtract an x from both sides, this time I'll show that with the shortcut. I'm subtracting an x from both sides. What I'm doing is I am taking this x and I'm moving it over to the other side. That's the way students like to describe it a lot. If it's positive x over here, it will be negative x when it moves over here. The -4 I'm keeping where it is because I wanted ax plus by equals c form. So all I was really doing was getting this x term over there. It's positive on the right side, it becomes negative on the left side. If we want to show the steps where we subtract x from both sides, we end up with the same thing. Okay, now I'm going to write these two, one right underneath the other. Negative x plus y equals -4. Now, when I add these 2 equations together, the x's aren't going to cancel and the y's aren't going to cancel, because I didn't get lucky this time and have an x term that's the same size but the opposite sign as the x term in the other equation, and it didn't happen with the y terms either. The next trick with elimination is to multiply one of the equations, and sometimes both, with whatever numbers I need to make that happen. And I realize all I need here is to multiply the second equation by 2. Multiplying an equation by a number is fine so long as you multiply everything in the equation by that number. So if I multiply everything in the second equation by 2, I get -2x, which is what I wanted, because it will cancel with this 2x when I add them later. But the y becomes positive 2y, and the -4 becomes -8. This is a little messy, so I'm going to write my 2 equations over here. Equation 1, 2x plus 4y equals 8. Equation 2 has now become -2x plus 2y equals -8. And I'm adding these 2 equations. 2x plus -2x cancels. That's what I wanted. So I don't have to write an x in my answer. 4y plus 2y is equal to 6y, and 8 plus -8 is equal to 0. Okay, that's strange, but should I panic? No. I have to trust my algebra, and I have to realize that I'm not finished because I want my y to be isolated. So since my y is being multiplied by a 6, I'm dividing both sides by a 6. These cancel, y is now isolated, I go all the way to the end, but 0 divided by 6 is still equal to 0. So what I found out is that y is equal to 0. And if you remember the answer we got when we did this system with the graphing method, y was equal to 0. And this is why we shouldn't panic when this happens. Y equals 0 is a perfectly good answer. So in our answer, after the comma, I'm putting a 0. I have to find out what x is. We all know what x is going to be because I already did it with the graphing method, but we're going to go through all the steps that are necessary with elimination, because sometimes you don't graph the situation first and then do it again with elimination. Often you just look at the situation and you go straight into elimination. So what do we do now? We want to know what x is equal to, and we'll find out by plugging y equals 0 into one of the equations, whichever equation we want. So I'm going to use the y equals x minus 4. If y is 0, I have 0 equals x minus 4. But I want to get this 4 over to the other side, so my x is isolated. So I am going to add a 4 to both sides, showing all the steps this time. These cancel. X is isolated, and 0 plus 4 is 4. So I have 4 equals x, which we know means x equals 4. It means the same thing. So I have my answer, and it is the same answer we got with the graphing method. It works. The fact that we can do it with different methods and keep getting the same answer helps us feel confident in that answer. But I also want to do this system with substitution. So that's what I'm going to do next. Keep a look at the time. I think I'm doing okay with the time. So I will erase all this, erase that answer, which we know we should get again. I'm going to erase all of these extra steps of algebra that I did, and now I'm going to do substitution. In substitution, we look at our two equations and we see is either the y or the x already isolated in one of these equations. Not in this one, but in this one y is already isolated. So I am going to use the fact that y is equal to x minus 4 and substitute that x minus 4 into the y position in the other equation. This is actually going very quickly. If y is equal to x minus 4, I replace this y with x minus 4. And then I simplify. 2x plus 4x minus 16, be careful, it's a bracket, equals 8. 2x plus 4x is equal to 6x. And if I move the minus 16 to the other side, it becomes plus 16. I have 6x equals 24. I'm almost done. Divide both sides by 6. And x is isolated, and 24 divided by 6 is equal to 4. There we go. X is equal to 4. We kind of knew that was going to happen. Oops. We need to show what y is equal to. Even though we know what the answer is going to be, we're going to take one of the equations and we're going to replace the x with a 4. So I'll do it with this equation this time. 2 times 2x plus 4y equals 8 becomes 2 times 4 plus 4y equals 8. 8 plus 4y equals 8. Let's subtract an 8 from both sides. Oops. These cancel, but so do these. I have 4y over here. I don't have nothing over here. I have a 0 over on this side. I'm nearly finished. My y is not quite isolated yet. I'm going to finish my algebra by dividing both sides by 4. Cancel, cancel. Y is equal to 0 over 4, which is 0. And we kind of knew that was going to happen. The point 40 is the solution set for this system of equations, regardless of whether you use elimination, substitution, or graphing. This is how it usually goes. But like I said, there's a lot of variety. So there's some things that we can refer to as oddball situations. What are the other things that can happen besides what we've seen so far, where we get an x-coordinate and a y-coordinate when we do these methods? Let's try one of the oddball situations and see what happens. And that means I'm going to write my third system of two equations. And we're going to start working with it with the graphing method first again. I'll get rid of this page, so I don't need that page anymore. And here we go. My third system of equations. Equation 1 is 2x plus y equals 8. My second equation is y minus 4 equals negative 2x. And I want to get these into y equals mx plus b forms so that I can quickly graph them. That's not so difficult to do in this case. The y is here on the left where I want it. I just don't want the 2x with it. if I subtract the 2x from both sides, it looks like I am moving the 2x over to the right side, but it becomes negative 2x. And then we still have plus 8 over there. That quickly. And again, I'm doing the shortcut. I didn't show 2x minus 2x on the left side. Sometimes I show it, sometimes I don't. And at this point, I can start making my table of values, but I also have this one to deal with. I'm going to isolate my y in this one as well. And it's going to be very quick because I have only this minus 4 with this y. If I add a 4 to both sides, the 4's on the left side cancel, and I have y equals negative 2x plus 4. Notice how both of them have the same m. They both have the same slope of negative 2, but they have different y-intercepts. Let's graph. Table of values for the first one, table of values for the second one. I'll get my axes in place right away. Label them. I'm ready, let's go. If x is 0, negative 2 times 0 is 0, plus 8 is equal to 8. We have the point 0, 8. If x is 2, negative 2 times 2 is negative 4, and negative 4 plus 8 is positive 4. We have a second point. If x is 4, negative 2 times 4 is negative 8, and negative 8 is equal negative 2 times 4 is negative 8, and negative 8 plus 8 is equal to 0. We have our third point. Do the same thing here. If x is 0, negative 2 times 0 is 0 plus 4 is equal to 4. If x is 2, negative 2 times 2 is negative 4, and negative 4 plus 4 is equal to 0. And if x is 4, negative 2 times 4 is negative 8, and negative 8 plus 4 is negative 4. They're not identical tables of values, but filling them in was very similar for the two of them because the structure of the equations were so close to being the same. They aren't the same, but they were close. 0, 8, let's put 0, 8 here. That means 4, 0 should be about here if I'm going to be consistent with how I scale my two axes. And 2, 4, of course, is going to be right there, and we can draw a line. And I'll label it line 1. 0, 4 is going to be here. Remember, I made this 8, so that's going to be 4. 2, 0, it's going to be there. And 4, negative 4 is going to be about here. And when I draw a line through these points, it's messy, but I can see that it looks like I have parallel lines. And the truth is, when two lines have the same slope, it makes sense that they're parallel, because the slope, of course, is the thing that determines how the line is tilted. They're both tilted the same way, they have the same m. So I'm not too surprised to see that they're parallel. But what happens with parallel lines as far as the solution set? That's strange. This is an oddball situation, because these lines, parallel lines, never cross. If they never cross, I can't give a point where they cross. So what I have to do for my answer is I have to say parallel lines, no solution. There can be no solution because the solution is the point where the lines cross and these two never cross. That is an oddball answer to an oddball question. But it is one of the things that can happen when you have a system of two linear equations. So we have to know how to deal with it when it does happen. This is how we deal with it when it happens graphically. What about when the same situation happens and we're trying to do elimination? Good question. So let's find out by doing it. Remember, parallel lines, no solution. That was our answer. To do elimination, what do we want? We want ax plus by equals c form for both equations. This one's already in that form. This one, not quite. If I move the negative 2x over to the left and move the minus 4 to the right, I can get it into ax plus by equals c form. So what I'm going to do first is subtract a y from both sides. That's not what I'm going to do first. Sorry. Please allow me to back up, beep, 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 and just not subtract a y from both sides. I want the y to the left of the equals, which is where it already was. What I'm going to do is I'm going to add a 4 to both sides. These cancel. Okay, so I have the 4 over here where I wanted it, but the negative 2x has to be moved. I now have y equals negative 2x plus 4. If I add 2x to both sides, I will have 2x plus y equals negative 2x plus 2x plus 4, and these cancel. Is this going to fit? Yes, it is, just barely. I have 2x plus y equals 4 on the right as the result of my algebra, and it is now in ax plus by equals c form. I'm going to write them together to set up the elimination. First equation, 2x plus y equals 8. Second equation, 2x plus y equals 4. Now to do elimination, I need either the x's or the y's to cancel when I add the two equations together. But that's not going to happen here because all of these terms are positive. But a quick trick to making that happen, since both of these x's have a 2, both of the y's have a 1 as the numerical coefficients, is to multiply one of the equations by negative 1. And I show it like this. I'm multiplying by negative 1. The first equation I'm not changing. The second equation, when I multiply it by negative 1, becomes negative 2x minus y equals negative 4. We're nearly there. Let's add the equations. But 2x plus negative 2x cancels. And y plus negative y also cancels. All that I have on the left side is 0. 2x plus negative 2x equals 0, and y plus negative y also equals 0. It doesn't mean there's nothing there, it means there's a 0 there. But 8 plus negative 4 is positive 4, and I have the statement 0 equals 4. And this makes no sense. The algebraic solution of elimination gave me a statement that makes no sense. But the fact that this makes no sense makes sense because these are parallel lines. So when you're doing the algebra methods to solve a system of linear equations, when you get a statement that makes no sense, it means the lines are parallel and there is no solution. The fact that it makes no sense makes sense. I've always kind of liked that. What's going to happen when we do substitution? Can you predict? When we do substitution, will we get a statement that makes no sense? We should, because we know already that the answer is going to be parallel lines, no solution. But let's find out by doing it. So we're going to do substitution with this same set, this same system of equations. And I'll erase all my algebra, because the algebra doesn't necessarily look the same when you're doing substitution as it does when you're doing elimination. For substitution, I want one of the variables to be isolated in one of the equations, like isolating a y, for instance. So how about I decide that if I subtract 2x from both sides of this equation, it doesn't matter if I write 8 minus 2x. In this case, I'm not trying to create a y equals ax plus b form, so if I feel like putting the x term over on the right, I can. These cancel. I have y equals 8 minus 2x. Of course, I could have written y equals negative 2x plus 8. It still would have worked. But if y is equal to 8 minus 2x, it means that this y is equal to 8 minus 2x. So I'm going to write this equation again. Y minus 4 equals negative 2x. I'm going to replace the y with 8 minus 2x. Okay, we're getting there. Now we have that thing that we always want to get whenever we do substitution or elimination, which is we turned our system of two equations with two variables into a single equation with only one variable. And now we simplify. 8 minus 4 is 4. But I want to get the x's all on the same side of the equal, so I'm going to add 2x to both sides. Need more chalk. These cancel. My 4 is isolated on the left side, but these also cancel, and that doesn't mean there's nothing over here. It means I have a 0 over that could happen again. We got a statement that makes no sense. Makes no sense. Now, you don't have to write the phrase makes no sense when you are answering a question like this. I'm writing it because I want the students to notice that the algebraic solution gives you a statement that makes no sense as a clue so that you can write the correct answer, and this is the correct answer. Parallel lines, no solution. And again, we see that these methods all work because we use 3 different methods: graphing, elimination, substitution, and they all gave us the same answer, just like in the first 2 systems of equations that we dealt with. That's 3 systems of equations we've done in about 45 minutes, getting to 45 minutes, which means that my timing is pretty good. I have time to do 1 more system of equations, and again, I'm going to do all 3 methods. Are there any other oddball situations that can happen? I can think of only one other oddball situation that might happen. So I'm going to try to make it happen so that we can see how it looks. And that means I need my equations for my last example. Aha! Now I remember this one. Equation 1 is x plus y equals 5. That's a quick, easy one. Equation 2, 3y minus 15 equals negative 3x. Okay, that one's a bit of a mess. Let's graph. To graph, we want y equals mx plus b. If I subtract x from both sides of this equation, I have these cancel. Y, oh, I wrote it backwards. Y equals 5 minus x, but I prefer to write y equals negative x plus 5, so that I have y equals mx plus b form. And I can start building my table of values. I'll do that right away this time. If x is 0, if x is 0, negative 0 plus 5 is equal to 5. If x is 2, negative 2 plus 5 is equal to 3. And if x is 4, negative 4 plus 5 is equal to 1. Very quickly, we have a table of values. Now this one, to get this into y equals mx plus b form, well, I need to move the 15 over to the right side. So I'm adding 15 to both sides. These cancel. 3y equals negative 3x plus 15, but my y is not isolated yet. I have to divide everything by 3 so that I can cancel these. Now y is isolated. Let's see if it still fits on the chalkboard wall in the video rectangle. Negative 3 over 3 cancels to negative x, and 15 over 3 is equal to 5. I have y equals negative x plus 5. But wait, that's what I had the first time. So here's what other oddball situation can happen. Even though it didn't seem obvious when we first saw the 2 equations, it turns out that they're really the same equation. So a system of 2 equations where both equations are the same, what's that going to make happen? Well, I can tell you one thing. I don't have to do a second table of values very much, do I? Because I realized that this table of values must work for this. But let's say I didn't notice that, and I just started to do it, and I didn't choose all of the same points. If x is 0, I really like to use x equals 0 as one of my points. Negative 0 plus 5 is equal to 5. I still am not noticing that I'm getting the same table of values, but what if instead of using a 2 and a 4, I chose a 1 and a 3? I might not notice that I'm getting the same table of values, the same line. If x is 1, negative 1 plus 5 is equal to 4. If x is 3, negative 3 plus 5 is equal to 2. It still doesn't look exactly the same. Let's graph it though. If I decide to put the point 0, 5 here, 2, 3 should therefore be about here, and 4, 1 should be about there. And I can draw a line. Now, and that's my first equation. Now I'm trying to graph this one. 0, 5, well that's in the same spot. 1, 4 would be here, and 3, 2 would be there. And I'm starting to see that the dots are all landing in the same line. How am I going to do this? I'm going to draw another line through the same bunch of dots, but I'm not drawing it very perfectly because I'm trying to make it that we can see that there are actually 2 lines there. I drew two lines, they just landed in the same place. Now the answer, that's going to be the trick. What's the answer? With parallel lines, there was no solution because the two lines never crossed, so there was no point that they held in common. But we can see a lot of evidence that with these two lines, all of their points are in common. So how do we say that? The term that we want is coinciding lines. Coinciding means that they are landing in the same place. And then the answer, an infinite number of solutions. Is there any chalk left in this other chalk holder? I'm getting really low on chalk with that one. An infinite number of solutions ends up being the solution set. Infinite? Really? That many? We can see, looks like we have 5 solutions that are in common with the two lines, but we realize the way straight lines work that all these other points in between these ones, over here, over there, are also going to be on both lines. And we also know that both lines go forever in both directions. And then we start to feel, yes, there has to be an infinite number of solutions for this system of two equations. It's two equations, but it was really two of the same equation. And when you answer a question and this happens, it's not necessarily obvious when you first look at the equations, because we can use algebra to change the positions of anything we want in a straight line. We can multiply a straight line by any number we want. So we can make an infinite number of equations that really can all simplify into this same equation. That's interesting. But what I still have to do is try elimination and substitution with this system. And I have just enough time to do that, so I'm going to erase my graph. Erase most of my algebra. Just keep the original equations. Now let's do the elimination method. Okay, for elimination we want ax plus by equals c form. This one's already in that form. This one, not quite. So I'm going to add a 3x to both sides. But these cancel. So over here I have just 0. 3x plus 3y minus 15 equals 0. I almost have the form of the line I want. It's this minus 15. I want that on the other side. So I'm going to add 15 to both sides. Oops. Write the minus 15 first. Then I'll write plus 15 equals 0 plus 15. These cancel. I have 3x plus 3y equals 15. And I don't want to write this low on the chalkboard wall anymore, so I'll move it up there. 3x plus 3y equals 15. That's my second equation. This one's already in the form ax plus by equals c, so I'll write my first equation like this. X plus y equals 5. I almost forgot that I had a dog sitting right over there. She's still there. Very well behaved little dog. Okay, but I want to add these together, and I want to either the x's or the y's to cancel. How am I going to do that? If I multiply this first equation by negative 3, I have to multiply every term in it by negative 3, and if I do that, the first equation will turn into negative 3x minus 3y equals negative 15. Then I just rewrite the second equation. And when I add these cancel, that's 0. These cancel, that's 0. And these cancel. I end up with 0 equals 0. And this makes a lot of sense. So with parallel lines, I ended up with 4 equals 0, or you could get negative 12 equals 0, or 0 equals 20. You get a statement at the end of the algebraic method with parallel lines that makes no sense. But 0 equals 0 makes perfect sense. I'm even going to write makes sense with an exclamation point. My answer, when you get a statement 0 equals 0, which makes perfect sense, and it's always 0 equals 0 when you do elimination with coinciding lines, then you know, I got 0 equals 0, therefore coinciding lines, and yeah, it takes time to write this, the words are long, but it's worth going because you want to give a complete answer. An infinite number of solutions. Yeah, takes a while. But coinciding lines will do this when you do elimination with them. What will they do when you do substitution with them? After all that writing, here I am erasing already. This is the last example. And it's the same two equations, but with substitution this time. How do I set up substitution? I need either x or y isolated in one of the equations. That will be faster to do with this one than this one. So I am going to isolate the y in this equation by subtracting an x from both sides. Because I am not graphing, I am not trying to make y equals mx plus b happen, I can write 5 minus x or negative x plus 5. Either way it is correct. These cancel. Y is already isolated and it's equal to 5 minus x. I'm trying to make that look good. Okay, that means this y is equal to 5 minus x when I do my substitution. So I take my other equation and I write it again, but I substitute 5 minus x for the y position. Simplifying, 3 times 5 is 15. 3 times negative x is minus 3x. Just doing my algebra, going ahead and doing algebra. I want to isolate my variable. I want to combine similar terms. 15 minus 15 cancels. What do I do when I want to move minus 3x to the other side in algebra? I add 3x to both sides. But these cancel, and so do these, and I end up with, a bit more chalk please, 0 equals 0, which makes sense. 0 equals 0 makes sense, and it tells me I have coinciding lines. Yes, it's worth the trouble and the time of writing it. Coinciding lines and infinite number of solutions. And we are done. We have done 4 different systems of linear equations. In each of those 4 systems, we solved it 3 different ways: graphing, elimination, substitution. In all 4 cases, the answers we got from the 3 methods kept on being the same, because all 3 methods work. Graphing may be the prettiest method and the most fun if you like getting out a ruler and a piece of graph paper. But with graphing, you have to sort of estimate that point where the lines cross. And if your lines are a little crooked, it might make you give your answer, it's a little bit off. It's still correct answer. It's a little bit off because you use the graphical method. But the 2 algebraic methods give you perfect answers every time. What's great though is knowing more than one method for doing the same thing, and realizing that when you use one method and you get an answer and you're not sure, you can try doing the system again with a different method and see if you get the same answer. And that gives you that power to know whether you're correct or not without having to check with anyone else. That is fun. From me and my dog, I am going to lift the dog up to say goodbye. Oh, she's heavy. She must weigh at least 14 pounds. Okay, from my beautiful assistant Mocha, who never really works on systems of equations very much. I've never seen her with a systems of equations book in her crate. And from me, Doug, I am very happy to say thank you for being with me this week. And I look forward to next week and the next lesson. Goodbye.